Hey, my name's Josh. Today we're going to walk through Email Buddy, which is a new AI agentic application made for navigating your own emails using the Jack programming language. So first of all, let's get into specifics of what is Email Buddy, right? So it was built with JackLang, which is a brand new language made to develop applications just like this, right? This project was made to transform your inbox into an intelligent knowledge graph that's easily traversable by AI agents with a simple web app interface. So it's just kind of making the whole experience of using your emails a little bit easier, right? So you can stop searching and start asking more questions. So why does Jack or JackLang specifically fit with the Email Buddy idea, right? So there's three main elements that serve of why Jack really fits Email Buddy. So number one is object spatial programming. This is a new paradigm of adding relationships between different objects. We'll get into the specifics in a second. But through that, you could build your own knowledge graph, and then you could have your own traversal agents moving through that graph to determine the best possible outcome. You have agentic programs using by keyword, which we'll talk about in a second. But these make the walkers or the agents more intelligent, and they can navigate through this graph independently. And then we have scale native, which allows API access to your backend. It also allows your backend to grow as user need grows. So you can not really have to worry about any of the architectural or any of the infrastructure switches when developing applications such as this. So first of all, what is OSP, or Object Spatial Programming, right? So OSP extends traditional object-oriented programming, which is really cool, right? So it doesn't remove any of the functionality of having different classes. Instead, what it does is it gives your classes or objects more meaning, right? So currently with object-oriented programming, you have member variables and you have member functions. So you have data and you have functions you could interact with the data on. But let's say you have two different instances of the same object, right? Or the same class. Let's say you have two different people or an email and a person. How do you represent person A sent an email to person B, or in this case, Maggie sent an email and then the email is delivered to Josh, right? These relationships are not super intuitive to design in object-oriented programming, but object spatial programming makes it really easy to navigate and to make a knowledge graph such as this. So again, like I said, with Email Buddy, we have different nodes or different objects that we can assign values to. In this case, we have a person node, which is a name and an email, and then we have an email node, which has as a sender, as recipients, as a date, subject, email, and then an email UUID we assign to it. And then with object spatial programming, we can create these objects, and then we can say Josh created an email, and that email was sent to Sarah and John, and then John created an email and it was sent to Josh, right? So you can create these little arrows representations between the different nodes that in object-oriented program you can't really do very easily. On a high level, what Email Buddy is doing, right, is we're taking just a JSON file that's formatted in our particular expected input. Look at the repo if you want specifics on that, but it'll parse that into its own node data structures, sender, recipients, and emails. We treat sender and recipients as a person node, but the way they're related to emails of what direction the relation's pointed in, you can almost identify them as a sender or recipient. If we go back here, we'll see when Josh sends or creates an email, right, you can see that Josh points to the email, and if you receive an email, the email points to you, right? So while there's only one person node, or one person class or object type, we have multiple different ways of representing these people through the way other nodes interact or point to our current node. We're then going to ensure that if you have one person, such as, again, Josh, right? Let's say you have one guy named Josh and you have 10 different emails sent to Josh. I don't want to make 10 different Josh nodes. I want one Josh node with 10 emails pointing to Josh, right? To avoid any duplicates, we're going to connect all the nodes to the root, which we'll explain in a second. The root node is just a globally accessible node that we could use to help navigate our graph. And then we're going to create some more of the directed relationships like we just discussed, with having a sender point to an email and an email point to its recipients. And then once we do all these steps, we'll have a fully connected graph that we can traverse, we can search, and we can have any queries we want to get more information about our emails. So what exactly is our root node, right? So as you can see here, this is an example, a very basic example of how you create some people nodes and then an email. you're just creating like any other class. Just you're calling your constructor with your own inputs. In this case, we're just giving it a name. We're then going to connect all of these nodes to the root. So that kind of looks over here where you have all of your nodes pointed to root. And then after that, we can make some of these more connected or direct connectivity relationships. So Josh points to email points to James. In this case, we have Alice points to email points to Bob, or Sarah points to Sup points to Josh, right? So you're able to make more connected of a graph based off of these interactions. Having all of your nodes, or at least all the initial nodes you want to be discoverable, point to root is important, because root node is the one node that is guaranteed to be able to be found by any walker. It just is a global pointer that helps navigate or orientate yourself while using your knowledge graph, right? So let's go into more about how to then navigate the graph we just created. So with that, we can use walkers, which is a new, again, object spatial programming notation of, it's instead of having your data flow through your functions, almost like functional programming, where you have your pipeline of data goes to function, goes to function, goes to function, and finally you have an output. We're instead having your function, or in this case, your walker, move through your data or your graph. So walkers are, again, mobile computational entities, or they're this ability to kind of have a programmable way of traversing through your graph. The way Email Buddy does this is, if you see here to the right, so if you see here to the right here, we have our find sender node. So what we're going to do here is we're going to check, we're going to give it a target. We're going to try to find a person node through that, right? So in this case, we're using a check for existing senders, emails or people or other people. We're going to start at the root node, as you can see here, and we're going to explore outward along connections and automatically stop when a match or condition is found. So here is how we define our walker. Again, so we have our target we're looking for. We have the person node when we eventually find it. We're going to set it to be none initially because we haven't found it yet. We can give it attributes or abilities to actually know what behavior it should be doing when given different node types on the graph. Again, reminder here with the root node, this is kind of, again, our global pointer. So we're going to start with our root. We're going to visit all of the connections that point away from the root. In this case, it's just going to be people. So we're going to add this attribute down here where it can search for all the people. So when entering a person node, this is the behavior you'll expect, right? So we'll visit all the nodes connected to the root. We'll discover all the people. If the current node or here matches the email of the target we're looking for, we're going to send here, which is, again, almost like the self keyword, but instead of it being for a class, it's for your node or your position on the graph. We're going to set the person node to be here. And they're going to disengage, meaning you're going to exit the walker and return back to the original program or function calling our walker. So an example of this, like actually implemented down here, is we have our find sender node where we're looking for John. Up here we're looking for an email, but pretend right now we're looking for the name John, right? So we're going to create a traversal walker. We're going to spawn the walker on root, which just means we want the walker to start at root. And then once it's at root, it can do the behavior we just explained, where we're visiting all of the connected nodes from root. And then when it disengages or it finishes, we're able to then find the person node that the walker found, right? If it didn't find anything, it's just a none type, and we can deal with that and following logic. But at a high level, we just made a way of traversing the graph and actually finding a node we're looking for, right? So next, let's go into more specifics on how to have some higher level behavior beyond just like search the way we just did. So we're going to be using agentic programming, specifically with the by LLM keyword. So what that means is, so first of all, again, what is an agent, right? So an agent is a system that observes its environment. It uses AI, often a large language model such as ChatGPT, Gemini, Claude, and it decides what to do based off of the environment it's observing, and then it takes the action it decides upon, right? So typically systems like that are used, when they're used like that, there is a lot of prompt engineering required. So a lot of instructing the large language model what specific behavior is expected. ByLLM takes away a lot of that and abstracts it, so you don't have to worry about most of the prompt engineering. Instead, you're able to just pass in the arguments to a function, and then the meaning of that function is inferred from the context of the input the name of the function, and then the doc string, and then the sem strings as well. We'll get into all that in a second, but at a high level, you're removing a lot of the need for prompt engineering with having the actual implementation inferred from the context at which you're programming. As you see down here, we import the ByLLM library. We're going to create a global variable that is the large language model. We're assigning the name or the type of model we're using. We're going to create our function. This is just a normal, again, way you'd create a function in Jack. In this case, we're defining translate to function. We're giving it the language you want to translate to. We're giving it the phrase that's going to be translated. We're going to be outputting a string. And instead of writing any implementation, we're just going to say by large language model or by LLM, right? And then with our entry, we're then able to just call the function as normal. So we're able to translate to Welsh. We're able to give it a phrase. We're able to take the output and then print the output like any other function. Again, this is really cool because normally you'd have to make a lot of implementation changes where there's more prompt engineering, a lot more overhead with the dealing of different models, libraries, but ByLLM abstracts most of that away for you. So why does EmailBuddy need AI agents, right? So when you have a large system with a lot of moving elements, especially with unstructured data, it's kind of hard to determine what the best course of action is. You can't really hard program that. So what these AI agents do is it allows you to have more of a dynamic decision making when you're navigating your database, especially graph databases, right? And it can understand the context it's looking for, trying to solve based off the user's input, right? So we're going to be tracking some sort of conversation history where we can see what the user just asked for. And then as the AI agent is exploring, it's able to then add more context to its own history to then better understand what it should be doing to answer our question. We're using agents for two different categories of help for the most part. We're using it for summarization and for navigation. For the navigation part, especially, you can see up here, you have a lot of different emails. It's kind of difficult to then decide what the best course of action is. So we're going to be summarizing these emails, then figuring out what the most relevant part of these emails are, and then navigating to our next node we're going to be exploring, right? So how do we do this? So with our summarization, we're going to import our library. We're going to, again, make our global large language model variable. We're then going to add a doc string. So this is just a small little string explaining what the function does. It's much shorter than, again, normal prompt engineering. It's like a small sentence. It doesn't need to be that large. Any larger is honestly overkill. In this case, we're just explaining very basically what the function should be doing under the hood. It knows already what the input variables are and what types the variables are, as well as the type of the output. So we don't have to explain any of that unless it's some interesting behavior, which we'll get into in a second. But if it's just expected behavior, you can just pass in all of the information normally, and then we'll just call down here our function, just like any other function, right? So we're presenting our options, we're giving it the previous context, and then we're just saying, let the large language model decide what the best summary is to get the most relevant parts out of our presented options. So once we get our summary, right, we can make more complex decisions. In this case here, we're going to be starting to navigate the graph. So the way we're going to be doing that is we're going to be providing the agent three different options it can pick from. Number one, it's going to be picking to select a neighboring node to explore. So if you're on a person node, you can explore all the emails you were sent or all the emails you have received. Or if you're feeling like I'm on a node and I'm not really getting a lot of context from the nodes around me, let me hop around the graph. So instead of being stuck in my local element, let's go back to root and then go find a node more useful to what we're currently looking for, right? So the way we're going to be doing this is we have a custom data structure to represent our output of what we're going to be sending out to deal with, again, what the selection is of the large language model. Here we have a new abstraction called sem strings or semantic strings. What they do is they allow us to assign meaning to specific classes or member variables. In this case here, we're giving a little bit extra context because, again, this may not be really clear what exactly the response is expected. So we're going to say response, the object type, is a structured response that's used by agentic traversal logic. Our option is our actual defining action. So is that going to be, we selected a neighboring node? Is going to be, I'm querying with random, or we're going to be using semantic keywords to find a more relevant node to jump around the graph. Or we decided, okay, we found enough context, we're done. We're going to actually just end the search and then just respond back to the user. We're then going to say here I want to be either the chosen node we just selected, we want new search query, or a final response to send back to the user, and then give a short explanation of why you picked the option you did, right? And then again here, a quick sentence explaining what exactly the intended behavior is. We set our function as normal definition, and then by LLM with the output type being response, right? And then we call the function normal, right? So again, this kind of abstracts away a lot of the need for prompt engineering. All of the typing is inferred, all of the information we pass to the LLM, it's able to get this information on its own. We don't have to worry about dealing with like different types. It could use the types it was passed and use the names of the variables to infer its own meaning of what it should be doing. Finally, what we're going to be talking about today is called scale native. Scale native is a methodology or an approach to designing your application to automatically grow with your demand. So there's no manual code infrastructure changes when your program is growing. And another interesting thing that is really useful is it turns your walkers into API endpoints. So you can have your front end UI interact with your back end through calling walkers, and then the walker can return the information you're requesting. So this way there's no real need to write API endpoints to then call your walkers and then do the action. All of that can be handled through the walkers themselves, which is really useful. And why does that fit Email Buddy specifically, right? So our current project is running locally on our own machine, but it can very easily be expanded to be running a cloud server. The system also has to grow over time as the quantity of emails grows or the amount of users grows. So having a adjustable and dynamic system really makes this process of developing your application a lot easier. So here's how to actually use Scale Native. I'm going to move my camera. So first of all, here's a high-level overview of what the actual program looks like, right? So we use Scale Native. We have a front-end GUI, so we have a front-end web page. We have our API, which is our two walkers. So we have a query walker and then our upload walker. Query walker can ask any questions. So what did John send me recently? Or upload walker, I'm uploading a list of new emails I want to be added to our knowledge graph. We have our root node, which is down here. Again, this is the only pointer to the graph that the walkers can always be guaranteed to find. So it could start out at the root, and then we have the graph below it. So we have what the walkers can discover after exploring the root node, right? So through this, we can call just jack serve and then whatever the name of your file is. For Email Buddy, it's server.jack. It's totally customizable to what you need, but think about this as almost creating your own API server through your walkers you just created. It gives you a lot more flexibility to then, again, have that front-end web page interact with your back-end without having to have a headache of how to make the API back-end yourself. And then let's have a quick little recap of what exactly we learned let's have a quick little recap of seeing what we learned today through this presentation. So again, first of all, object spatial programming, it's a paradigm to add relationships to your objects, right? So we learned how to create a knowledge graph using Jack. We learned how to then traverse that graph to get the knowledge we need to then make intelligent decisions. We learned how to make AI agents through ByLLM and how ByLLM simplifies a lot of the prompt engineering required when designing these agents, while still retaining all the functionality any other agent would use. We then learned how to use a scale native application, which provides a lot of that API implementation that allows the web app to interact with our agents. And then also we learned that it could be an accessible system that's ready to grow as your project's ready to grow without a lot of infrastructure changes on its own. So yeah, so thank you again for watching, and hopefully you learned something today about both Email Buddy and Jack. If you have any questions, please leave a comment below, and I'll get to it as soon as I can. Thank you again, and hopefully see you soon.